Mr. Brown here, and this is a bit of a supplemental video for dimensional analysis. I will go through some more questions and re-show you how, again, to convert SI units using the dimensional analysis or the factor label method. At the core of dimensional analysis is the idea that our units on our measurements can be subjected to the same mathematical operations as their associated numbers. So we can multiply and divide them just like we do the measurements that we are making. A ratio of two equivalent quantities expressed with different units is what is known as a unit conversion factor. So it expresses the relationship between two different measurements. And we can use that unit conversion factor to convert between the different units that we may want to work with. In order to do this, we have to ensure that all conversion factors are oriented in the right way to ensure that the appropriate units are canceled out, as well as the appropriate units being left to answer our questions for whatever unit is being asked for. You may have learned along the way somewhere how to convert SI units, say grams to kilograms or milliliters to liters, using a method of counting the number of jumps that are made on a chart of SI units. We can also use dimensional analysis as a tool to convert our SI units between the different units. And it's perhaps more useful to learn it this way because we can include this type of dimensional analysis in other more complex calculations and allow us to sort of simplify our calculations by inserting more steps in one calculation. And we'll see how that works later in some more complex problems. First, we're going to practice doing the dimensional analysis to convert between SI units. And to do that, we have the chart from the textbook from section 1.4 that shows us the relationships, that shows us the conversion factors between the different prefixes given to our SI units. Each row in this table tells us the conversion factor equal to one base unit. For example, we can see in the milli row, the milli has the small m prefix, so for instance, if we put the small n in front of the g, it becomes 1 milligram. If we look at the milli row on the table, we see that it has a factor of 10 to the negative 3. So we can interpret that as 1 milligram is equal to 1 times 10 to the negative 3 grams, because grams is the base unit. It is the unit without any prefixes on its symbol. We can write that relationship as either 1 milligram per 1 times 10 to the negative 3 grams, with the 1 milligram over the 1 times 10 to the negative 3, or we can write 1 times 10 to the negative 3 grams per 1 milligram. Both of those relationships say the same thing, and we can use that as we need in our dimensional analysis calculations to help us arrive at the units that we want to arrive at. We'll see some examples on the following slides. Here on this slide, we have our first example of an SI unit conversion using dimensional analysis. The question reads, you need 134.2 milliliters of isopropyl alcohol that has the chemical formula C3H8O for proper disinfection. How many liters is this measurement? I like to start these problems by writing down the amount that I know or that I'm given. I know that I have 134.2 milliliters of isopropyl alcohol. I'm going to multiply this by some conversion factor and try to answer the question, how many liters is this amount? I can see from the SI unit table here in the bottom that the milli prefix corresponds to a relationship of 10 to the minus 3. So what that means is 1 milliliter is equal to 1 times 10 to the minus 3 liters. Now I can arrange that relationship in both of the ways that I showed on the previous slide. 1 milliliter per 1 times 10 to the minus 3 liters, or 1 times 10 to the minus 3 liters per 1 milliliter. I need to decide which of these conversion factors I will multiply by in order to arrive at the correct answer in my problem above. Since 134.2 milliliters is technically on the top, it is over 1, anything divided by 1 is itself, then I will probably want to use the relationship that has milliliters on the bottom, there should be a liters here, and liters on the top. That will allow me to cancel the milliliters and arrive at liters. So I see that I should do 1 times 10 to the minus 3 liters per 1 milliliter. That way, when I make this multiplication through, because milliliters is found on the top and on the bottom, they will divide out and cancel each other. And I will be left only with the liters unit, which should give me my answer. If I use the calculator to do 134.2 times 1 times 10 to the minus 3, 1 times 10 to the negative 3, and I was really careful to put that scientific notation in parentheses to make sure that it treated it as a scientifically notated number. The calculator returns 0.1342, 0.1342 liters. And so the answer is there are 0.1342 liters in 134.2 milliliters of the isopropyl alcohol. You may be asking, is this the correct number of significant figures for this calculation? And the answer is yes. The relationship 1 times 10 to the minus 3 liters and 1 milliliter are exact relationships. We say there is exactly 1 times 10 to the minus 3 liters in exactly 1 milliliter. So they are essentially counts, and they have infinite significant figures. The only measurement that we have here is the 134.2 milliliters, which has 4 significant figures. So there should be 4 significant figures in your answer. Our next example says, you measure out 34.793 grams of iron oxide, Fe3O2, for an experiment. How many kilograms of iron oxide is your sample? So for this problem, we will again start by writing out the known quantity that the problem gives us, which is 34.793 grams of our iron 2 oxide. We need to multiply this value by some conversion factor and arrive at an answer in kilograms. Again, we'll look to the SI unit table for our conversion factor, and we look for the kilo prefix we see here. And it tells us that the relationship between the kilo prefix and the base unit is 10 to the third. So 1 kilogram equals 1 times 10 to the third grams. And of course, we can write that as either 1 kilogram is 1 times 10 to the third grams, or 1 times 10 to the third grams is 1 kilogram. I will probably need to use this conversion factor here in order to cancel out the grams by putting it on the bottom and leaving the kilograms on top, because that is the answer that I ultimately want to get to. So I will write 1 kilogram per 1 times 10 to the 3 grams. So now the math says to do 34.793 times 1 divided by 1 times 10 to the third. We can simplify that to 34.793 divided by 1 times 10 to the third when we punch it in our calculators. 34.793 divided by 1 times 10 to the third. And again, I was real careful to put that 1 times 10 to the third all in parentheses so that my calculator treats it like a scientifically noted number. The answer the calculator gives me is 0.034793. And the unit we should have, since the grams cancel, is the kilograms. Nothing is there to cancel the kilograms. So 0.04793 kilograms is our answer. And we see again, the relationship has exact or infinite amounts of sig figs. The given quantity has 5 significant figures, and so we have 5 significant figures in our answer. Here on this slide, we have our next SI unit conversion problem that we are going to approach using dimensional analysis. The question reads, you measure a 3.2 micrometer. The little symbol there for micro is the lowercase Greek letter mu. So you measure a 3.2 micrometer bacteria in a culture. How big is the bacteria in millimeters? This is a little bit more complex problem than the previous two because we're not being asked to convert to or out of the base unit. Both of the units in the problems already have prefixes, so let's look at how we could approach this problem. We know that we are asked to convert the 3.2 micrometers to millimeters. The SI unit table from our text gives us the relationship of every prefix to the base unit. So we may have to approach this as a two-step problem by converting micrometers to the base unit, meters, and then converting that conversion into our wanted unit, millimeters. So I will try to determine the relationships of both millimeters and micrometers to meters using my SI unit table here. From that table, I see the relationship of micrometers. 1 micrometer equals 1 times 10 to the negative 6 meters. 1 millimeter from my table equals 1 times 10 to the negative 3 meters. So I can use these relationships in a unit conversion style problem using dimensional analysis to convert from micrometers to millimeters. The first thing I will do is try to get rid of the micrometers. Since the only relationship I have with micrometers is this one, I will try to arrange this relationship into a conversion factor that will allow me to cancel micrometers. That means I will probably want to put the micrometers on the bottom. 1 times 10 to the negative 6 meters is 1 micrometer. If I were to stop there and cancel my units, I would see that I would be canceling out the micrometers, but my answer, if I were to stop there, would be left in meters. So I need to put another relationship in here that will convert from meters to millimeters. That relationship is the second one that I wrote down. 1 millimeter equals 1 times 10 to the minus 3 meters. But I need to arrange that so that the meters are canceled and millimeters are left over. 1 millimeter on top with 1 times 10 to the minus 3 meters on the bottom would allow me to cancel the meters and be left with the millimeter units, which is what my question should be in anyways. Now that all that's left is to do the math. So I can see that the problem tells me to do 3.2 times 1 times 10 to the minus 6 times 1, and then divide that all by 1 times 10 to the minus 3. So if I'm carefully typing that into my calculator, I will be sure to put 3.2 times parentheses 1 times 10 to the negative 6. Close the parentheses times 1 equals, and then divided by 1 times 10 to the minus 3, making sure to keep that 1 times 10 to the minus 3 in parentheses. And I see there that my answer is 0.0032. I didn't leave myself enough space, so I'm going to mark that out, 0.0032, and then I'll rewrite my units. It is millimeters. I just marked that out because I didn't have enough space. 0.032 millimeters, and we're given 2 sig figs to begin with. Our answer ends with 2 sig figs, so 3.2 micrometers is equal to 0.0032 meters. And that is how you do a conversion if you have units that already have prefixes, not converting to or from that base unit. Over the next few slides, we'll look at some other types of problems that can be solved using dimensional analysis. And while we work on these problems, we will show how we will convert with complex units, how we may convert one set of derived units to another set of derived units, for instance. We will talk about how to determine your own conversion factors using context from the problems and building your own conversion factors from that context. One of the ways that dimensional analysis can be used is to do things like approach the density problems that we solved earlier by the factor label method instead of memorizing a ton of formulas. We'll see questions that look like this for this type of problem. What is the volume of a sample of 456.3 grams of lead, considering lead has a density of 11.3 grams per milliliter? Now, we've already seen how to solve these problems using the density formula, but let's assume we didn't know the density formula and instead rather see this density for what it really is. It is a conversion factor. This conversion factor tells us that 11.3 grams of lead equals 1 milliliter of lead. And we've already seen how we can write those relationships either way that we want to. We can say that 11.3 grams of lead is equal to 1 milliliter or per 1 milliliter of lead, or 1 milliliter of lead per 11.3 grams of lead. Provided we keep all the numbers with the correct units, we can write them in either of those ways that would help us most. And so if I'm making this conversion, this dimensional analysis, if you will, I will write out the number that I am given for the problem. I may give myself some room here. And we will see, we're told that our sample has a mass of 456.3 grams. We're going to multiply that by one of our factors so that we're left over. The question is, what is the volume? So we probably want our answer to be in milliliters, since liters and milliliters is a measure of volume. 456.3 grams, and then I'll need to multiply it by the relationship that cancels out the grams and leaves us with the milliliters. That looks to be this relationship here with grams in the denominator. 1 milliliter is 11.3 grams of lead. So we see the grams would cancel out here, and we are left with the math of 456.3 divided by 11.3. Which would be 40.4 milliliters. And I would leave this problem in 3 significant figures, because in the density measurement here, the 1 milliliter is exact. However, the 11.3 is an approximation. That number could be more significant if it was measured with a better measuring device. And so we have to take that as not an infinite significant figure. It is just 3 significant figures. So I'll leave my answer with 3 significant figures. So the answer to this one is 40.4 milliliters. Here on this slide, we see another density problem that can be solved using the factor label or dimensional analysis method. What is the mass of 345.9 milliliters of vegetable oil if the density of vegetable oil is 0.91 grams per milliliter? So we start this like we like to start our dimensional analysis problem. We write down what we know, 345.9 milliliters. We're going to multiply that by some conversion factor that hopefully will provide us with an answer in grams, since the question asks what is the mass. The relationship that we're given is 0.91 grams per milliliter, and so as we've seen with our other dimensional analysis problems, we can write that as 0.91 grams per 1 milliliter of vegetable oil, or 1 milliliter of vegetable oil per mass of 0.91 grams. Now you need to use one of these relationships in order to cancel out the milliliters and allow us to arrive at grams, and I believe that will be this relationship here. So I will rewrite that, 0.91 grams per 1 milliliter. That will allow me to cancel milliliters, and it will give me grams. Carefully type that in my calculator. Looks like our density here only has 2 significant figures, 345.9 times 0.91 divided by 1. The calculator says 314.769, but I can only have 2 significant figures in my answer, so I would round that through 310 grams. 310 grams. We have another dimensional analysis example here, and as we read through this one, you may find that it probably doesn't sound very much like a chemistry problem, and it's not. It's probably more of a physics problem, or maybe even more of a regular everyday life problem, and it will demonstrate how dimensional analysis can be used to approach many different problems and situations. The question reads, how long will it take to drive from New York to San Francisco if the distance of the trip is 2,904.9 miles and your average speed is 53.4 miles per hour? And we may even notice on a cursory read that the conversion factor is somewhat written out in text here, and so we'll need to build our own conversion factor from the context that we're given in the problem. The problem is essentially asking us to convert from a distance and a speed to total time. It's asking us how much time will it take to drive this trip given a distance and a relationship known as speed. So we know here that we have 2,904.9 miles, and we want to convert that to an answer in some unit of time. How long will it take? And since the question doesn't specify what units it wants, and we already have a unit of time in our derived unit that is hours, we will try to find an answer in hours. And so the relationship or the conversion factor we're given is 53.4 miles is equal to 1 hour. So that's what your speedometer is telling you when you're going down the road and it says 60 miles per hour. That means you are moving at a rate of 60 miles for every 1 hour that you drive. We can use that as a dimensional analysis factor. We can say that 53.4 miles is covered in 1 hour, or we can say that 1 hour covers 53.4 miles. And we can use that in any manner that we want in our dimensional analysis in order to cancel out the units we don't want and arrive at the units we do want. So I will give myself a multiplication here. And I will probably use this one to get miles canceled out and left over with hours. 1 hour is equal to 53.4 miles. That will allow me to cancel out miles, be left with hours. So that's probably how I want to approach this problem. I'm told the math, therefore, is 2904.9 times 1 divided by 53.4. We can simplify that to 2904.9 divided by 53.4. And we see that the answer is 54.3988764045 by my calculator. We have 3 significant figures as our lowest amount of significant figures, so I will round that off to 3 significant figures. Therefore, the answer would be 54.4 hours. This trip would take 54.4 hours to drive across our great country. In this example, we see a dimensional analysis style problem that asks us to answer in a set of derived units. So we're no longer asked to answer in just one plane unit. We're asked to answer here in this case in meters per second. The question reads, how fast is a plane traveling in meters per second if the speedometer reads 835.2 kilometers per hour? So what we're being asked to do in this problem is to take the measurement 835.2 and convert that to kilometers in 1 hour and convert that to some number in meters per second. So I need to find some multiplications that will allow me to get rid of the kilometers and hours and convert them to both meters and seconds and be in the right position when we are done. I have to think about the relationships that I know in order to build my own conversion factors for this problem. So I know that I may want to start with the relationship between kilometer and meter. If I go back and look at the SI unit charts, I could determine that 1 kilometer is equal to 1 times 10 to the 3 meters. So that is a useful conversion for this problem. So is 1 hour equals 3,600 seconds. Now I know that from 60 seconds per minute times 60 minutes, so 1 hour is 3,600 seconds. So now I can use these relationships, build conversion factors, and find a mathematical function that would get me from kilometers per hour to meters per second. I will probably start with the kilometers relationship. I know that I want to cancel out kilometers on top and be left with meters on top. So I will say 1 times 10 to the third meters is 1 kilometer. That would allow me to cancel here, and I would be left with meters on top, which is fine, which is what I want. I will also need to multiply by this relationship. The 1 hour is 3,600 seconds, in order to cancel out the hours and be left with seconds. But notice this time, hours is already on bottom here and I want it canceled out. So I will probably want to use it on top, which is lucky for me because that will put the seconds on the bottom, which is exactly what I want. 1 hour is 3,600 seconds. And then if I cancel my hours, I'm left with meters here, check, and seconds on the bottom, check, which is what I want my answer in. It's simply a matter of doing the math now, punching this in my calculator. I will do 835.2 times 1 times 10 to the third, wrapped up real tight in parentheses, times 1. And I'll divide all of that by 3,600. 1 times 3,600, but that's 3,600. And the answer is 232. That'll be 0.0 meters per second. 232 meters per second. This question is a good example of a more complex dimensional analysis problem. It will really test your ability to determine with the correct orientation of your units to cancel out units and arrive at the right answer. The question reads, how many minutes will it take a plane to fly from Raleigh to Chicago, which is a distance of 805.8 miles? The plane is traveling at a rate of 550 kilometers per hour, and there are 1.6 kilometers in 1 mile. So let's try to find a string of relationships that will help us convert miles to minutes given this information. If I start with the fact given that there are 805 miles in between, 805.8 miles in between Raleigh and Chicago, I know that I will want to get rid of the miles unit for sure. So I might start with the relationship that there are 1.6 kilometers in 1 mile. And that would allow me to cancel out the miles, but all that does is tell me how many kilometers the trip is. Luckily for us, we have an average rate of speed in kilometers per hour. So that will allow us to convert our kilometers to hours, essentially. We won't be done, but we'll be closer. Since kilometers is on top here, I'll want it to be on the bottom in the next conversion. So 550 kilometers per hour rewritten in the correct form for our dimensional analysis would be 1 hour is equal to 550 kilometers. That would allow us to cancel kilometers, but it would leave us with hours if we were to stop there. And we have read that our answer is asked for in minutes. So we'll need a conversion of hours to minutes. This is one that we will probably be asked to know on our own. This is not one that's going to be given to you. There are 60 minutes in 1 hour. Hopefully you know that conversion. You may have never set it up in a dimensional analysis style problem before, but you do know that there are 60 minutes per hour. And if we cancel there, we can see that the unit left over would be minutes. And so we would essentially convert miles to minutes by way of an average speed of kilometers per hour. The math that we're asked to do is 805.8 times 1.6 times 1 times 60 divided by 1 times 550 times 1. So and turns out the total flight time would be approximately 141. If you round everything off, it comes to 141 minutes on a flight from Raleigh to Chicago at an average rate of 550 kilometers per hour. Now, that would be a pretty fast commercial plane, but not out of the realm of possibility, I guess. Here on this slide, we have another dimensional analysis problem, and this style of problem probably sounds a little more chemistry focused than some of the speed problems. It also will highlight why chemistry is an important science for those that want to go into the allied health sciences, nursing, pharmacy, etc. This kind of really shows some of the practical applications of chemistry in those areas. The question reads, how many milligrams of a drug does a 72.3 kilogram patient need if the dosage calls for 3.5 milligrams of drug per kilogram of body mass? And so we're given a measurement and then a relationship to convert that measurement to another value. We can see from the question that the given measurement is a 72.3 pound mass, kilogram mass, or sorry, yeah, 72.3 kilograms, not pounds. The 72.3 kilogram mass is going to be multiplied by some relationship. We can see that the drug has a relationship of 3.5 milligrams per kilogram, and we could write that 1 kilogram per 3.5 milligrams or 3.5 milligrams per 1 kilogram. And in this case, that is what we want to do because that will help us cancel the kilogram part of the formula per 1 kilogram of body mass. And I will write this in 1 milligram, 3.5 milligrams of drug per 1 kilogram of body mass. It kind of gives you a little more visual as to what these numbers actually mean. When we're mixing those units of mass, it can get a little confusing. And so kilograms of body mass cancels with kilograms of body mass, and that leaves us with milligrams of drug that needs to be delivered. And we can see that the math there calls for 72.3 times 3.5 and then divide the whole result by 1, or just leave it alone if you want to be a little simple about it. 72.3 times 3.5 tells us that this patient needs 253 milligrams, 253.05 milligrams of this particular drug. And if we round that off with significant figures, that would be 250 milligrams of the drug in question. Here on this slide, we have another problem that asks us to convert from body mass of a patient to how much drug the patient should receive. This question really kicks up the difficulty of the problem up a notch. It asks us to do multiple conversions in one problem, but it highlights how dimensional analysis is able to simplify a multiple conversion problem. The problem here reads, a colloidal solution of amoxicillin is commonly provided to children for treatment of bacterial infections like otitis media. If a patient with a body weight of 25 pounds is provided with a preparation of amoxicillin at a concentration of 250 milligrams per 5 milliliters, how many milliliters should one dose be if the doses are to be divided into twice daily? 1 pound is 2.2 kilograms, and the common dosage is 30 milligrams per kilogram of body mass every day. And so we start with what we know. We know that the patient weighs 25 pounds. All of the technical information is given to me in SI units, even though I weighed the patient in standard imperial units, so I may start with that conversion, figuring out how many kilograms 25 pounds is. So dimensional analysis tells me that I need to get a relationship with pounds on the bottom and kilograms on the top. And so I will write 2.2 kilograms is 1 pound, using this relationship here given to me in my problem. That will allow me to cancel out pounds, and that would tell me how many kilograms the patient weighs. But I'm not going to stop there. I'm going to get rid of the kilograms using the fact that I should give the patient 30 milligrams of active ingredient per 1 kilogram of body mass. If I were to stop there, I would figure out how many milligrams the patient needs of this active ingredient every day. But that doesn't really tell me a whole lot because I have a liquid with the active ingredient in it, and I need to measure that liquid out in milliliters. So I will use the next relationship that tells me that every 5 milliliters of solution has 250 milligrams of active ingredient. But since I want the milligrams to cancel out, I'm going to put it on the bottom. So 5 milliliters of solution has 250 milligrams of active ingredient. And so if I were to stop there and calculate, it would be 25 times 2.2 times 30 times 5 divided by 1 times 1 times 250 for a grand total of 33 milliliters. And I do notice that some of my measurements here have only 2 sig figs, so I would probably round that to 2 significant figures and say that one dose should be 30 milliliters. But if I'm being very careful, that would be 30 milliliters for 1 whole day. If I'm being very careful, reading my problem closely, I notice that the final piece here says divided into twice daily. So one dose should be 15 milliliters. And that is how we can do a multiple conversion problem in one step or one set of steps using dimensional analysis.